Hello, my dear friends. In the last lecture, we have derived a differential equation for a one-dimensional body. Now, in this lecture, you'll get the idea on differential equation for a three-dimensional body. To derive the differential equation for a three-dimensional body due to a heat flow in a volume. Now, consider a small element is a solid body having a dimensions dx, dy and dz along x, y, z direction respectively as shown in figure 1, this one. So in the previous derivation we have insulated along y and z direction, but here in a three-dimensional body the element is subjected to a heat flux in all directions of a Cartesian coordinate system. You can see here heat flow along x direction q of x and heat leaves by the system along x direction q of x plus dx. Heat entering along y direction q of y leaving q of y plus dy. Heat entering along z direction q of z, heat leaving along z direction q of z plus dz. We know that the energy balancing during time dt can be stated as heat flow in to the system. Heat inflow plus heat generated is equals to heat outflow plus change in internal energy. We know that heat inflow E dot in plus E dot G is equals to E dot out plus E dot in energy balancing equation we have learned and based on the law of conservation of energy, where q of x, q of y, q of z be the heat inflow along xyz direction. In the previous case we have taken only q of x and now we are taking a q of x, q of y, q of z, all the values. Instead of taking a capital Q heat generated by the system, we have taken here a q dash. The q dash, small q dash be the heat generated by the system, where you can see here q of x plus dx is equals to qx plus dou qx divided by dou x into dx. Similarly along y direction heat outflow q y plus dy is equals to qy plus dou qy divided by dou y into dy, and qz plus dz is equals to qz plus dou qz plus dou z into dz, or the heat outflow along xyz direction. Rho is the mass density of the material in kg per meter cube. Cp is nothing but a specific heat of the material joules per kg Kelvin. dt, d capital T is a rise in temperature difference, where a of x is nothing but a of x dz into dy. A of x where the heat flow will take place along x direction from this surface, this is a dx. Heat will get entering to this surface which is dy and dz. That means a of x is equals to dz dy. Similarly a of y, bottom face of the parallelepiped, if I'll take this one is an a dx, this one is an a dz, where the heat enters along y direction q of y and moves with respect to y direction, that leaves in the y direction, and that surface is also along dx and dz. See here a of y dx dz. Similarly, and a of z dx dy, area along the surfaces with respect to qx, qy and qz. Now that equilibrium equation will take here, you can check out heat inflow, heat generated and heat out of flow plus change in internal energies. Change in internal energies we have and heat inflow q of x plus q of y plus q of z into dt plus q bar is nothing but a heat generated in a whole volume dx dy dz into dt is equals to q of x plus dx plus of q of y plus dy plus of q of z plus dz, heat out of flow in a volume into dt, and change in energy, internal energy, that within the volume density rho into cp dt into dx dy dz. Within the volume of this element, specific heat will be generated due to change in temperature throughout the density of the element. Now we got this will remains the same as it is, only this will be get changed. I will take this value on a left hand side, then that rearranged equation, you can see here q of x minus q of x plus dx, q of y becomes q of y minus q of y plus dy, q of z minus q of z plus dz. See here, when I'll take this on a left hand side, we'll have here q of x minus q x plus dx, q of y minus q of y minus q of y plus dy, q of z minus q of z plus dz into dt common for whole the values. This as it is we have taken, and this as it is equals value we have taken, call it as equation number 2. Now I will consider this value, then we'll find these values. This will be remain same. Want to find out these values which is entering the heat into the volume of the system, and leaving by the volume of the system. Just we'll considering a along x direction. First we'll find the conduction heat transfer effect under differential equation of equilibrium will bring, then we'll go with the y and z direction. To find a q of x minus q x plus dx, consider a heat flow through a body along x direction. We have this q of x is equals to minus of kx a dou t by dou x. We know this equation, just we need to input this value into the equation. Then q of x plus dx, q of x plus dx, we are very well known, qx plus dou qx divided by dou x into dx. Then this value which is equals to q of x, we have this one, and q of x plus dx minus of this value. So directly we'll take here. So instead of substituting this value, I have remains same. This q of x, q of x, q of x will get cancelled when I'll remove these brackets. Only will remains minus of dou qx divided by dou x into dx. This value is equals to this one. And then after rearranging that equation, now we'll substitute the value of this q of x in this equation. Otherwise these equations will become very lengthy. Well, we'll substitute directly that values in that equation. To avoid such types of lengthy equations, very simple equations we have taken. After eliminating the final equation, we are substituting the value of a q of x here. The q of x which is equals to minus of kx a dou t by dou x, minus sign is there, minus sign, it becomes plus, into dx will remains as it is here. Then I'll take as a dou by dou x, similarly k of x into dou t by dou x. I'll take I'll take outside, that a value is equals to dz and dy, a value where the heat inflow will takes place, and heat is moving along x direction d z and exiting in the same direction. Now area of cross section A is equals to along x direction dou dy by dz. Dy by dz I have taken here, and then rearrange this one. Equation becomes dou by dou x k of x dou t by dou x dx dy dz. All the values we got, call it as equation number A. Similarly along y and z direction, q of y minus q of y plus dy, just these values in terms of a y, dou by dou x becomes dou by dou y, k of x becomes k of y, dou t by dou x becomes dou t by dou y, dx dy dz. Call it as equation number B. Similarly along z direction, only this where the x is there, this will become z, this will become z, and then this will becomes dou z. Rest of the values will remain same here. You can see just one drive the equation, and similarly you get the all directional equations. Then substitute this all equation A, B and C into the equation number 2. in this equation number 2, this is equation number A, equation number B, equation number C, substitute those values, this will be remains as it is. We'll have here modified equation for heat flow along x direction, modified equation heat flow in a volume along y direction along z direction into dt. Then this will be remains as it is. We'll take now dt will take a common, then this will be move inside the bracket, and I'll take a dx dy dz. See here, dx dy dz, dx dy dz, dx dy dz, dx dy dz into dt we can take out from this whole equation in the left hand side. So I'll take this here, I'll take this as it is here, and then I'll take this as it is here, plus of q bar into dx dy dz into dt small t, it is with respect to time, is equals to, we have this as it is, internal energy changed Cp d capital T change in temperature into dx dy dz. The left hand side dx dy dz, on the right hand side dx dy dz will get cancelled. This is not a time dependent variable, this is a time change in time, this is a change in temperature, don't cancel it carefully. Just I will take on the right hand side, I will take dt along right hand side, then this equation is as it is. I have taken after eliminating this dx dy dz on the left hand side, dt I'll take on the right hand side, rho cp as it is, d capital T divided by d small t. Capital T means temperature difference, dt means variation of a time, that is a temperature gradient. Call it as equation number 3. Then equation number 3 is a differential governing equation for three-dimensional heat conduction in an orthotropic solid body. This one is in an orthotropic solid body. This equation is satisfied for orthotropic material. This equation number 3 is satisfied for a orthotropic material, not for a isotropic material. We'll solve the problems on isotropic material, so we need to bring that how the isotropic material will take place. You can see here now for a homogeneous and isotropic material, where this kx, ky and kz is called as an k, conduction heat transfer along xyz direction, all the values of the conduction is remain same for isotropic material. For orthotropic material, in all direction it is different. Okay, then I'll take k is common here, then dou by dou x into dou t by dou x we have here. Similarly, dou by dou y into dou t by dou y we have here. Similarly, dou by dou z into dou t by dou z we have here, plus q bar is equals to, this will be remain same. This equation is satisfied for the isotropic body, and then I will differentiate this value becomes a dou square t by dou x square, dou square t by dou y square, dou square t by dou z square, plus of q bar equals to cp d capital T by dt. Call it as equation number 4. We know that the Fourier equation for thermal diffusivity alpha, where we know that alpha is equals to k divided by rho into cp. Fourier's equation gives as a thermal diffusivity alpha, which is equals to thermal conductivity divided by density into specific heat. This is the equation for a diffusivity. The mathematically is been defined. Then we have the value here, rho into cp. When I'll take this k on the left hand side, this becomes rho cp divided by k, reverse to this order. Then 1 by alpha is equals to this rho cp divided by k, so which will be satisfied for this equation. I'll rearrange this equation. I'll divide k on both sides. For equation number 4 we'll get this one, k will get cancelled for this characteristics as it is. I have taken plus of q bar divided by k is equals to rho cp divided by k into dt. This value which is equals to 1 by alpha, replace that value here, this will be remains as it is, and then this becomes a 1 by alpha into temperature gradient. Call it as equation number 5. Then For a steady state condition, equation number 5, LHS becomes 0. For steady state, this change in internal energy of the system is equals to 0. Call it as equation number 6. Then this equation number 6 is called as a Poisson's equation. For a steady state without any heat source, there is no heat generated by the system, then this equation number 6 will be yields to this Q of bar is equals to 0. Q bar is equals to 0. There is no heat will be generated. Then this differential equation of equilibrium for a three-dimensional body under no heat generation under steady state condition, which is equals to dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square is equals to 0. Call it as equation number 7. Then this equation number 7 is said to be as a Laplace equation for heat transfer. Thank you for listening my lecture.